Good afternoon, and thank you for the introduction. As said, I'm Jakob Feldkeller, and I present our work BasicBlocker. And this is a contribution to the question of how to react to the detection of speculative execution attacks like Spectre. And this is a joint work with Jan Philipp Thoma, Markus Kraus, Tim Ginesu, and Daniel Bernstein. And so I guess most of you have a quite decent understanding of how a processor works, but so I hope you excuse me if I repeat some of the basics just to make sure all of us are on the same page. So modern processors don't execute an instruction, so they don't execute the instructions one by one, but rather they have features like pipelining and out-of-order execution and branch prediction to make the execution much faster and to gain performance. And so I will go into the details a bit more now. And so, as I said, the CPU is pipelined, which means that we have several stages where an instruction goes through them one stage after another, so that we have multiple stages, multiple instructions in different stages at the same time. And the first stage is the fetch stage, where we simply fetch the instruction from the instruction cache and insert it into the pipeline. And the second stage is the decode stage. And here we try to understand what kind of instruction we have. So which resources do we require? Do we need the arithmetical unit? Is it a memory access instruction, or is it a control flow instruction? And basically, in this stage, we have two types of control flow speculation. And yeah, I forgot to mention this. I will focus in this description to the features related to control flow speculation, because this is what we focus in this work on. And so we have two types of control flow speculation here. Basically, so the first thing is something that we call speculative fetching. And this is that due to the fact that only after the decode stage, we know whether we have a control flow instruction or whether we have some other kind of instruction. So only after the decode stage, we know whether the next instruction in memory is also the next instruction that we need to fetch, or whether we have some other instruction that we need to fetch somewhere else in the code. And but most of the processors just fetch the next instruction in memory, regardless of the type of the instruction they currently have, because they don't know which kind of instruction they have. And if it's wrong, then they just fetch the next the right instruction and throw this instruction away. And I want to highlight here that there is no actual attack that we know of that exploits this type of control flow speculation. So there is some kind of rather specific theoretical attack that has some specific corner case in SGX. But yeah, so this is not really an security issue that we know of, but still, to be secure, we consider this as something that might be exploitable in the future. So we take a conservative approach and think this off as insecure as well. And the next type of speculation, the second type, is related to branch prediction. So this is what we normally mean when we say control flow speculation. So this is branch prediction, where we don't know whether a branch, an upcoming branch that we decode here, whether this is taken or not taken. So we just guess which one we take. And of course, there are some good heuristics on how to guess, but simply we guess. And if it is right, then we can continue later on, and otherwise we have later on to reverse it. And similar things you can do with indirect jumps, where you guess the target instruction. Then the second, or the next stage, or multiple stages, is then we have multiple stages that deal with management of out-of-order execution, which is just to improve the performance by utilizing the resources of the CPU more effectively. Afterwards, we have the actual execute stage, which can consist of multiple stages actually, or is often multiple stages. And here the actual execution of the instruction is done, which means that we give the data to the arithmetical unit, or we access the memory, or stuff like that. And also in this stage, we figure out whether our prediction of the branch predictor was correct or false. And if it is false, then we need to reverse everything that we did until now. and start again with the correct instructions. And if it is right, then we can just continue and have gained a lot of performance. And afterwards, we have, again, some stages that deal with out-of-order management, bringing everything back in order again. And finally, the write-back stage, which write everything back to the register file, and which then means that it is indeed visible to the software layer, so to the architectural level. And so now an instruction is considered executed from the software point of view. And then, so this is how roughly a CPU now works. And then famously, Spectre exploited speculative execution to reveal secret information from some internal secrets from another process. And they do this by basically mistraining the branch predictor so that the branch predictor will always, or with a high probability, predict the wrong outcome. So it will go into the wrong direction in the code. And then in this speculative realm, an out-of-order memory access is performed that is dependent on the secret value. So we have now the microarchitecture, which is dependent on some secret. And the microarchitecture is the changes in the hardware that is not accessible to the memory yet, to the software yet. And then the software figures out that, okay, or the CPU figures out that this is what's wrong, so this was speculatively. It will reverse most of the changes it had done, but not everything. And so the attacker can recover the secret through a side channel from the microarchitecture, and in this specific attack, they use a cache side channel. And afterwards, after this attack was published, we had a lot of other attacks that work similarly, using speculative execution to exploit a lot of programs, and also other types of speculation. So, for example, data speculation was also used. And where we have attacks, we also, of course, have a lot of countermeasures. So a lot of countermeasures was proposed as well. And so this is the basic playing field where BasicBlocker works in, or is laid in. And while most, or I would say all of the other countermeasures try to make speculation more secure by either separating the non-speculative and the speculative world more clearly, so adding more resources to it, or defining which kind of behavior is dangerous and then avoiding this kind of behavior. Our work tries to do a different approach. So the main reason for speculation is really performance. So we try to figure out how we can make a CPU faster if we don't use speculation in the first place, which would mean that the CPU is secure against such type of attacks, and we don't need to define what is a secure behavior in the first place, which is of course evolving because of the arms race between attackers and defenders. And so if we look at again at how software is executed in the CPU when we have no speculation at all, so also no speculative fetching, then indeed it is quite slow, because we always have to wait until the decode stage was done before we can fetch the next instruction, because only after the decode stage we know whether the next instruction or whether the current instruction is a control flow instruction, so whether the next instruction in memory will be fetched or not. And if we have a branch instruction or some other kind of control flow instruction, then we have to even wait longer until after the execute stage, because only then we really know which is the new instruction. And the problem here is that the CPU is really unaware of the general code structure, and that we only know the current instruction in the current execution stage, or wherever we are at the moment. But if we look at the compiler level, then we have a much more holistic picture of the control of the code structure, because we have there the control flow graph, which consists of basic blocks, which are really blocks of straight line code where we are guaranteed to have no control flow changes within them. So what BasicBlocker does simply, it makes the CPU aware of those basic blocks by introducing a new instruction that has as a parameter the size of the upcoming basic block. So quite simple. And what we can do then is when we start executing a basic block, we can fetch this basic block. And here we assume that after the decode stage, we know the size, so this parameter, because we have then decoded the basic block instruction. And we also assume that we have non-zero basic blocks, because that would make no sense. So this is why we can fetch, after the basic block, we directly can fetch the first instruction of this basic block. And afterwards, we can fetch each instruction one by one until we have consumed the entire basic block. And I want to note that this is also true if we have multiscalar processors. So we have where we have multiple ways in the pipeline, so we can fetch 2 instructions, for example, at a time. Here we have to wait a little bit because we have to again decode the BB instruction before we can fetch the second instruction of the basic block, but after then we can really utilize the entire ways of the pipeline. But of course, this does not work if we have 2 consecutive basic blocks. So here we would first need to execute the first basic block, then have to decode the last instruction of the first basic block to ensure that to know whether this is a branch or not. So we have to wait until the decode phase, and then we can fetch the BB instruction of the second, and afterwards we can continue executing the second one. So to make also this transition between those kind of 2 basic blocks more efficient, we add another parameter to the BB instruction, which is the flag, which states that the basic block is something that we call sequential. And by sequential, we mean that the next basic block in memory is also the next basic block that will be executed. And so this also means there is no control flow instruction in the basic block. And what we can do then is we start executing the first basic block, and after we have decoded the basic block instruction of the first basic block, we now know the size of the basic block, so we also know, and that it is sequential, so we also know the location of the next basic block that we want to execute, so we can fetch the BB instruction of the next basic block, and then continue executing the first basic block. When this is consumed entirely, then we have also decoded, in this example, we have decoded the basic block instruction of the second block, so we can just continue with the second block without any stalling of the pipeline. But of course, this only works for consecutive basic blocks that are sequential, but not if we have any control flow instruction. But we then observed that when we have this basic block instruction, we don't really need a branch and control flow instruction to terminate a basic block, because we already know how much instruction are in the basic block. So we can just shift the control flow instruction up in the basic block, and how much ever the data dependencies allow us to shift it up. And in this case, we then can do something similar as with sequential basic blocks. So we can start executing the first basic block after we have executed now so we have, well, on the execute stage of the control flow instruction here, the branch instruction, we now know the real instruction that will be executed after, or the basic block that will be executed after this basic block. So in this loop, for example, we would know that it is again, the BB instruction of this basic block. So we can again fetch this basic block and then continue executing the first iteration of this basic block, and then we have decoded the basic block instruction of the second run, and so we can continue again with the with the second iteration. And through this, we can really execute a lot of code without any stalling of the pipeline, as long as we have basic blocks that are large enough to either do this interleaving of the basic block in the sequential case, or if we have control flow instructions, then we can upshift the basic block, the branch instruction far enough. So, but how does this look in real-world applications? And for this, we implemented this in 2 types of processors. We first used the Vextrus 5, which is a rather small in-order 5-stage pipeline. processor, which is soft core, so we can execute this in real hardware. And we have a simulator of Gem5 where we also implemented our work, which is a bit more complex, though they support superscalar pipeline of WIS2 and have an out-of-order execution and 6 stages. Sorry. And we also implemented our thing into the LLVM compiler framework to do this insertion of basic block instruction automatically. Sorry. And here you see the performance comparison of the different variants, where we give the relative performance to the baseline of a CPU that doesn't know speculation at all. And in blue, we have the variant that does control flow speculation, though this is a normal implementation that Vector 5 in this case has. In gray, we have the BB info so the BB, the basic blocker variant with no rescheduling of branch instructions, and in green, we have the BB variant with rescheduling of branch instructions. And here, lower is of course is better because this is relative the relative overhead, so to speak. And as we can see, there are a lot of benchmarks where control flow speculation really is better than basic blocker, but we also have some cases where basic blocker is equally good or even better than control flow speculation. And then we did have the same graph for the Gem5 implementation. Sorry. There's water. Okay, thank you. Maybe I'll take some. So for the Gem5, and we have a similar picture here. So we have first some where basic blocker does not perform as well as branch prediction or control flow speculation at all. And we have some cases where we have a similar outcome. And if we look more closely into the structure of the code, where we perform good or not good, then we can see that, so these are the dynamic basic block sizes of the code we execute, which means that we weight the size of the basic blocks by the number of executions that they are executed. And here we see those where we are quite good at have really large basic blocks. So it is what we would assume that if we have basic blocks that are large enough to do this interleaving, then we really are good. And we can have good performance. And this is supported by this graph, which shows how much we can upshift the control flow instructions. And again, we see those where those benchmarks where we are quite well, where we have good performance, we have a large degree of upshifting. So to conclude, Basic Blocker would allow trivially secure CPU against control flow speculation-based attacks, because we don't have any control flow speculation, and we allow fast execution for optimized code, which is code which has large basic blocks. So in future work, one could try to increase the size of those basic blocks or the relation between branching and basic block size, and do this either at the algorithmic level. So, for example, using sorting networks instead of other sorting algorithms, because there we have less branching. It can be used by doing supporting hardware loop counters, where you just tell the CPU that there is a loop, and then the hardware takes care of executing the loop. And we have preliminary results already in the paper. And you can, of course, do linearization like conditional moves. And we have still some space left in our base block instruction. So you could also add other information to the base block instruction to either make the performance better or achieve other security goals or stuff like that. Yes, so that's from my side. Thank you very much. And I'm happy to take any questions.
Okay, okay, I think there are questions on the side, so
No.
I'm still here, sorry.
I was thinking if
No.
Anyway, should I get the microphone for that? Please, right?
That's it, because we are recording.
Sure, that's why. Okay. So I was wondering whether you actually compared your performance with the speculative execution.
Yes, the blue graph.
Because I haven't seen it. So
So here the blue graph is the speculative execution.
okay.
This is the speculative execution, and the green and the gray are ours, and the red baseline is no speculation at all.
Okay, awesome. So basically you said that this solution would work actually when the basic blocks are pretty large.
Yes.
So in general, like I have seen that in the benchmarks you have checked.
Yeah.
Like there were actually like not a lot of applications that had very large basic blocks.
Yes.
So, how would you see this thing in real world applied? Because at the moment, maybe like basic blocks are smaller. What would you do to actually improve the performance there?
Yes, so this is a bit what I refer to in the future for future work. So these benchmarks are really without any changes to so this is just the software as we would write it now, without any consideration of basic block size, so to speak. And but for example, the case of sorting networks shows there are, at least for a lot of applications, I guess, algorithms where you can really increase the basic block size compared to the state of the art or basic algorithm, basic solutions. And also we have some preliminary results again in the paper in the appendix where we, transfer some of the benchmarks that we have to be more optimal in our cases. So this should be possible in a lot of cases, but yes, so this is not a solution that has generally good performance for all kinds of code as it is now for control flow speculation, where you can have just throw arbitrary code nearly into the CPU and this performs quite well. But yes, you have to, while programming, you have to be aware of this, yes.
Sorry. That's all right. So can you actually do the two things at the same time? Can you use BasicBlocker and control flow speculation?
Yes, but
Of course, it's not secure.
Yes.
But you could do that, right? So basically, your technique is just a way to optimize the speed of the code, so then you can sort of get what we already had in terms of performance without doing the speculation. But as a bad, CPU designer, I could take your approach and just use that on top of control flow speculation to get even better performance.
You can, of course, do this. So at the moment, speculation, at least if you look at CPUs like from Intel or stuff like that, speculation is really good. So you have, I don't know, a rate of 96% correct guesses. So yeah, I don't know how much, so it certainly might gain some performance even on top of this, yes. But yes, as you said, it's not secure, so it's a bit going around our point.
No, I understand, but my point was more that your solution is not to solve basically the attack, the speculative attack. It's just to improve the performance in general. It's an orthogonal thing.
Yes.
But by doing that, you can sort of, motivate the industry to say, okay, we don't need to do, CFG just because we can get similar performance or at least better performance than what we can do now. But there are two orthogonal things. Yeah,
so it is not, our proposal is not in itself a defense mechanism against speculation, but rather so normally you would not consider removing speculation from the CPU because the performance cost is so high, as is shown in here, for example, between the red and the blue graph. And this is what the motivation for this work, to say, okay, if we have no speculation, how could we still be quite efficient in the execution? So yes, it is more, if you would say, a countermeasure against the loss of not doing speculation.
I would like to provide an answer to your question whether we would gain more performance if we would have the normal control flow speculation and would add BasicBlocker on top, not regarding security at all. The thing is, I get the good performing programs, probably they would improve. But the thing is, with BasicBlocker, we add additional instructions. For each basic block, we have a new instruction. This is quite of an overhead depending on the program. So you might even lose performance by adding both. Depending on the program. Yeah,
yeah, that's true.
Any more questions? Okay, let's move on to the third paper, fast intro.